Hi, I'm Natalie. I'm a PhD candidate working with Rob Evans at Hui. And yeah, I'm just going to be talking about a magnetotelluric survey that was conducted in 2021 of the Gofar Oceanic Transform Fault and what we can say about the distribution of fluid around the fault. So there we go. This is the Gofar. It's here near 5 degrees south on the EPR. And I'm just going to outline the plate boundary in white. It's sort of a little bit complicated. Here's the ridge, and then the fault is split up into these three strands. So these are the active parts of the fault, and these features extending away from them are just fracture zones, not seismically active. This fault has been used as sort of a model transform fault. There's been a lot of research here to understand the behavior of transform faults sort of in general. Um, so one interesting feature of oceanic transform faults is that they tend to have relatively low coupling. So this is an image from a 2004 study where they took all of the global oceanic transform faults and they predicted essentially the area on each fault that's cold enough to rupture seismically above the brittle ductile transition. And then they've plotted here on the x-axis that sort of predicted area that could rupture against, on the y-axis, their estimates based on measurements of large earthquakes from a global seismic network of the actual area that seems to be rupturing seismically. And there's some scatter. Each of these points is a transform fault, but they found that on average, the faults tended to follow this gray line, which represents about 15% of the expected area actually appears to be rupturing seismically, which means we have a lot of aseismic slip happening. Most of the slip is accompanied aseismically. And just for reference, there's the Gofar, that's where it plots. It's a pretty representative transform fault. Another interesting property of oceanic transform faults is that they tend to have variable coupling along strike. So this is an image, these are images from Sheedall 2022. And so you can see here that the bathymetry around the transform fault, and these red dots are their relocated earthquake epicenters. And so they used these earthquakes to estimate the moment rate as a function of distance along each transform fault. And so that estimate is this pink curve here. That's the moment rate along moving along strike of the transform fault. And then this green line is the expected moment rate on the transform fault. And you can see that in some places, the calculated or estimated moment rate is comparable to the expected moment rate. But in these gray regions, the calculated moment rate is way below the expected moment rate. So it looks like in those places, the fault is experiencing a lot of aseismic slip. And so there's this variability along strike, which raises the question, you know, what controls coupling on an oceanic transform fault if we see this variable behavior? And there are a number of factors that could theoretically control coupling on these faults. And in this talk, I'm going to be focusing on fluid in the rock around the fault zone. And specifically, the question we want to address is like, empirically, do we observe a correlation between fluid content in the fault zone and seismic behavior, like in natural fault zones, right? So we chose to focus on the Gofar specifically for a couple of reasons. The first is that it has really clear variability in seismic properties along strike. So these are the locations of large earthquakes, magnitude greater than 5.5, on the Gofar over the last couple of decades. And for reference, the largest earthquake that's ever been recorded on the Gofar is a 6.3. So I'm going to focus on this like western strand here. You can see there's this little cluster of earthquakes over here. These earthquakes tend to rupture about every 5 years. It's like semi-periodic. And then we also get earthquakes nucleating over here, and there also are these like sort of 5-year recurrence intervals on these patches. But then in between, we have this gap where we haven't nucleated, as far as we know, any earthquakes greater than a magnitude 5. Um, and there's a lot of microseismicity here. So the pattern in microseismicity looks different on this section of the fault than it does on these other sections. The microseismicity is shallower. We also, in 2008, collected some detailed seismic data around this section of the fault and recorded a large earthquake over here. And prior to the earthquake, there was a ton of microseismicity in this area. And then as soon as the earthquake happened, it all shut off. So It's definitely kind of a distinct region seismically on this fault. And it finally also is a barrier to the propagation of large ruptures. So if an earthquake nucleates over here, it's not going to be able to propagate over to this half of the fault. It'll get sort of stuck in the rupture barrier. So we call this area the rupture barrier, and these areas, like the asperity zones, because they're hosting large earthquakes. And yeah, it's just a really good example of this variable coupling along strike. The other reason that we focused on the Gofar is that there's just a ton of data from this area to compare our data to. So this is the location of an active source P-wave tomography study from Roland et al. 2012. We have a gravity study here from Pickle et al. This is ship track. We've got basalt samples, so we have some geochemical information, and this is the location of the 2008 OBS deployment. There was also a later OBS deployment just focused on the rupture barrier, and we have high resolution bathymetry data. So it's just to say there's a lot of data, great context for our results. So to these data sets, we are adding an EM survey. So these are our instruments. They're mostly focused on the rupture barrier, but they extend a little bit into the asperity zones on either side. And we chose to use EM to learn about the fluid in the fault zone because EM methods are sensitive to the electrical conductivity of the subsurface. And seawater is about 5 orders of magnitude more electrically conductive than dry crust rock, right? Basalt or gabbro. So this just shows that seawater conductivity, even pretty cold seawater, is out here near 3 Siemens per meter, whereas dry oceanic crust is like 5 orders of magnitude lower. And we see about 3 orders of magnitude change in the bulk conductivity of the rock for a reasonable, range of porosity values. So we're quite sensitive to porosity with EM methods. You can also use seismic methods to think about porosity, and people have done this actually at the Gofar. So these are results from Emily Rowland's 2012 paper, where this is from the active source survey that I showed on the previous slide. So these are estimates of porosity from P-wave tomography with depth in the fault zone. And you can see there are 3 curves here, and each curve represents a different value of alpha, which is the pore aspect ratio. And so you can see that, varying the pore aspect ratio or your assumption of the pore aspect ratio by a couple orders of magnitude gives you a pretty different estimate for porosity. So, these results are very useful, but it's also helpful to have an independent data set to sort of narrow down some of this ambiguity. Oop. So this is our final 3D conductivity model from our survey. So yellow here is conductive and blue is resistive. So we would expect higher porosity areas to look yellow. And you can see the location of the block diagram on this map up here. So this face that we're looking at is running along the fault. And we can see already that there's this high conductivity, so apparently high porosity region sort of along the fault. So it's higher conductivity here than it is north of the fault, right? Or off to the sides of our survey. This here is the barrier zone, and I've highlighted it on the map as well. And so the high conductivity anomaly is largely located within the barrier zone. But it's not perfect. There's a little bit of mismatch between the location of the barrier zone and the conductive zone, which is kind of interesting. I also just want to note that I've cropped my model at like 4 kilometers depth. We're actually sensitive to structure much deeper than this, but the lower crust in this area, interestingly, is extremely conductive, and I believe it's maybe not due to fluid. So since we want to focus on the fluid story, I have limited our interpretations to sort of the shallower parts of the crust, where it's more likely that what we're actually seeing is due to fluid. Okay, so I'm going to zoom in on this little rectangle along the fault so that bathymetry is shown up here, contoured, and then this line here is the fault trace as identified by Paige Koenig in her master's thesis. And I'm going to stick on underneath the corresponding profile through our model along the fault, right? And here's the rupture barrier, extends from here to here. So we can see this correlation between kind of deep bathymetry here and irregular fault trace and high conductivity in the top 4 kilometers. And I want to use this model to estimate porosity, right? So what we're going to do that, we need to know what the conductivity of the pore fluid is. So we've made our best estimate for the conductivity of the pore fluid based on temperature profile from numerical models from Mark Bain and Emily Rowland. And then we're using a formula for the conductivity of an NaCl fluid with approximately the salinity of seawater as a function of pressure and temperature, so as a function of depth in the crust. You can see the fluid will get more conductive as it heats up, going down, and then when it starts to transition to a supercritical fluid, the conductivity will kind of level out and start to decrease. So now we can use Archie's law, which tells us that the measured conductivity, so the colors on this plot, is equal to the conductivity of the fluid, which we've estimated here, times the porosity, that's what we want to know, right? Raised to this m exponent, which is dependent on how well connected the pores are. So there is some uncertainty here. We kind of have to make a guess for this value. But we know that typically in natural rocks, m ranges from 1.3 to 2.5 or so. And we chose to use a value of 1.5, which represents relatively well-connected pores for a couple of reasons. One, we're in a fault zone, so the crust is likely fractured, which tends to increase connectivity. And two, choosing a well-connected value gives us a conservative estimate for fluid content. So using Archie's law, we've contoured the model with our inferred fluid content. And this assumes that fluid is the primary conductor in the crust here. It's certainly so many more or so much more conductive than the sort of normal lithology here, that's usually a pretty decent assumption. And so yeah, you can see we have a couple volume percent fluid in the western part of the rupture barrier and pretty negligible fluid in the easternmost rupture barrier. Okay, now on top, I've put the earthquake catalog from the 2019 to 2021 OBS deployment focused on the rupture barrier. We can see that there's some heterogeneity both in the conductivity structure within the rupture barrier and in the spatial distribution of microseismicity. So these earthquakes are scaled by magnitude. And just to give you a sense for sort of their distribution in space, I've projected them onto this flat plane, but actually the distribution is quite three-dimensional. The fault zone is relatively wide here. It's about 2 kilometers wide. The earthquakes measured in 2020 look like this, and these are the ones measured in 2021. Pretty different, but in both cases, quite complex and three-dimensional. Okay, I want to focus on this sub-region of the rupture barrier here, because this has the greatest conductivity, so the highest inferred fluid content. It also has the greatest number of small earthquakes measured during this deployment, 18,000, similar to this section over here, but much higher than sort of the peripheral parts of the rupture barrier. And the earthquakes are smallest here on average, so the B-value is highest to a statistically significant degree. So we seem to see a correlation between, apparent fluid content according to the EM and lots of very small earthquakes in this location. And so maybe we can start to tell a story where there's some transtension across the fault that causes distributed faulting, which allows seawater to infiltrate into the crust. And we see evidence that it's infiltrating at least down to 4 kilometers, maybe deeper. And then this seems to be correlated with abundant microearthquakes. So maybe what's happening is the water is altering the rock to materials with low coefficients of friction or that are velocity strengthening, which was limiting event size. There's also evidence in this area that there are aseismic transients, so probably fluid migrating through the fault zone, which tends to be associated with earthquake swarms. So these are a couple mechanisms for fluid promoting lots of microseismicity and even creep in this area. And then sort of separately, we have this question of like, why does this area broadly arrest large ruptures, right? So one way you can arrest rupture is to have a stepover in a fault. And we see that here. There's this approximately 1 kilometer wide stepover in the middle of the rupture barrier. Um, it's probably too small based on the limited numerical modeling that I've been able to find. This is probably too small to geometrically arrest rupture all on its own. But we may also have, fluid that this sort of associated transtension is allowing to penetrate into the crust, altering the rock to materials that are velocity strengthening, which can promote a seismic slip rather than seismic events and can arrest rupture. People have also proposed dilatancy strengthening as a mechanism for arresting rupture in this area. So dilatancy strengthening is a process that is co-seismic, so it happens on a short time scale. Essentially, you assume that in your fault zone you have some porosity, and then during an earthquake, you get some expansion of that space. So the pore space increases, which means that if you have the same amount of fluid, the pore pressure goes down, which increases the effect of normal stress and can kind of clamp the fault shut and can arrest rupture co-seismically. So this is a model run by Liu et al. 2020, where they replicated the rupture arrest in the Gofar transform fault by increasing the efficacy of dilatancy strengthening in a section of the fault that's about the same width as the rupture barrier. And they assumed about 5% porosity in the rupture barrier, which is similar to our results, at least for the western part of the rupture barrier. I don't know of definitive evidence that this process can only take place in areas with relatively high porosity, but to a first degree, our results are consistent with theirs. So zooming back out, if the story is that transtension has sort of allowed fluid to infiltrate in the rupture barrier and that's lowering coupling, we might expect this to be a common property of oceanic transform faults because many transform faults have low areas of low bathymetry along the fault that have been interpreted to reflect some transtension across the fault. So this process could potentially explain some of the global seismic deficit that I mentioned at the beginning. There's some outstanding questions. We seem to see this correlation between low coupling, high conductivity, and low bathymetry. But, is this typical? We just have this one observation. Is this typical? Unfortunately, I can't answer this question because we only have conductivity data from the Gofar, but maybe one day. It's also hard to pinpoint what specific mechanism accounts for the seismic deficit. We're observing this correlation, apparently, between fluid and low coupling in the rupture barrier. But that correlation is consistent with, alteration to weak or velocity strengthening minerals, changes in pore pressure, and potentially just a more complex fault network that is promoting smaller earthquakes and letting fluid in. So it's hard to determine causation from our observations. And finally, if this easternmost part of the rupture barrier is as fluid poor as it looks in our survey, why does it exhibit so much shallow microseismicity that is temporarily correlated with the microseismicity in the rest of the barrier zone? This is still sort of a mysterious kind of mismatch in those data sets. So some acknowledgements. Thank you to everyone who went on the cruise, which does not include me, unfortunately. I started my PhD right after this cruise. And yeah, any questions?